So we've got our sample network put together. We're going to briefly go over all of the setup that's needed to run a computation. So that includes setting up some of the automated design constraints, if that's the route we wanted to go. Engineering standards are basically custom warnings, setting up different scenarios. If you wanted to run multiple storms or versions of networks, there's ways to customize that. Validating the network before running it and reviewing results in flex tables. So we have a caution in the guidebook of the automated design is really just a preliminary look at things, and it's the designer responsibility to verify the results and they meet all the criteria. And I think we've discussed in previous TAC calls that the design priorities embedded in the Bentley engines are not necessarily the same priorities that FDOT would detail in the guidebook. So for these purposes, we're going to run through an analysis, but the setup for design is pretty similar. So I think our example is you're going to go into the software and do it, but here's just a quick overview of what the default design constraints look like. It's got tabs for each element and just a few settings on if it were going to automatically design this for us, what are the guardrails that are put up for it to follow. And engineering standards are basically a set of if-then statements. So if I have an 18-inch pipe and it's greater than 300-foot length, do I want it to warn me that, I'm not meeting some particular FDOT criteria? So this is not necessarily automatically populated, or it doesn't have a whole list that would aid designers. So this was one of the possible topics of discussion today is that something that's valuable and important to provide? It'd really just be above and beyond what the normal warnings would produce, but the database kind of capabilities and how this is written would allow us to put in some standard warnings if we so chose. But we can wait.
Looks like Adriana has a question, possibly.
Oh. Go ahead, Adriana.
I think you're still muted. Or you can type it in the chat if you like. Oh, she says she's good. Never mind.
Okay. So moving on to scenarios. This is a manager window that helps you define more than just a design or analysis that would have been typically available in geopack drainage. You can save different versions of storms if you want to run a 3-year storm and a 10-year storm, but not have to lose the results from either to go back and forth. This is a way to do that. So the scenarios are basically an umbrella that house a whole slew of alternatives. And by default, everything is set up as a base. So active topology uses base active topology. But if you wanted to make any changes, isolate certain parts of the system, tweak something here or there, you can create another alternative just for that element and make a new scenario to show just the change for that element should you want to. So one of our examples is we're going to create an alternative So instead of just using the zone 2 3-year rainfall, we're going to create an alternative that shows the 4-inch spread rainfall. So yeah, kind of touch base on the different alternatives that are available to tweak the calculations or scenarios. And I'll briefly touch on what each of these are. Topology is the list of all the elements. So let's say I had 5 different networks in this file and I wanted to run just one of them. I could isolate that specific set of structures in the topology for the scenario. There's some user data extensions, alternatives. I don't think that'll necessarily be a completely useful thing, but it is there in case there's tweaks that people want to make for those. There's a physical alternative. This comes up if you ask the software to do an automatic design. It'll warn you that there's likely going to be some physical changes to your pipe sizes or inverts, and if you want to save your previous version that you had by default before designing, this is the way to do that, is it'll create a physical alternative. So my next kind of question to the group to ponder is, when we get to the point where our models are deliverables, and down the road when folks are building drainage elements from these models, we may want to think about how we handle scenarios in different versions of networks so that there's not potential for building the wrong one. But really, this is just a design file for now, and it'll be pretty clear from our plans production, which one needs to get built. But just some thoughts on how we want to handle the deliverable for the final model. Do we want to just clear out any of the working analysis alternatives and just hand over what's actually proposed? So if you, moving down the list of alternatives, there's boundary conditions. If you want to run different versions of the tailwater that's being controlled. Is it your pond or is it the crown of pipe? This lets you keep various scenarios but then run more than one. So we're going to do an example in the rainfall runoff alternative. Head loss, this is another one if we want to run with or without minor losses. There's another example of where an alternative would be used. All right, calculation options. That's a little bit more along the lines of what the specific versions of a design or analysis are. So is it using, it's a gradually varied flow rational StormCat engine, or do you want it to run a swim engine or other types of calculations? It sets the controls on how it calculates, what are the parameters, that sort of thing. And there's quite a bit of properties that are up to edit. But to our best abilities, we've set it to run how an FDOT system would normally run. All right, and then before hitting the compute button, there's a validate tool that'll let you know if there's any errors in the system that are going to keep it from computing, and then there's a way to access all of the warning messages that may come up from before or after a compute. And the compute center is kind of a catch-all for all these tools where you can make some of the tweaks, and we'll get into that in the exercises. But although there is just a big green compute button, if you wanted to have a window to work through that dialog, it'll be available. And calculation summary, this window populates after a compute. The big takeaway is, does it say convergence was achieved? That means it was successful. And if not, the warnings and notifications will tell you what needs to be fixed. And then once you get into the details, it'll give you specific results for the various elements. Flex tables is where we've primarily put in the results for review. There's a flex table that mimics our storm tab as well as spread. And the profiles that we viewed earlier are another way to look at results, see how the system's performing. If you've got surcharge popping out of your inlets, seeing it visually is another good way to see how your system is designed. All right, so that was the quick overview. I'm going to jump into the actual design file. Does everybody have it open from the file we shared?
They need to have a thumbs up option instead of a hand.
All right, so let's just jump in. So exercise 3.1, we're going to review and set design constraints. So that is up in our analysis tab under analysis tools. So you'll see at the top there's 3 tabs, and then within each tab you've got sub-tabs to fill out. So a lot of this comes by default with the DGN library, but some of the input is project specific, and cycle through those. So velocity, minimum, maximum lines up with the drainage manual guidelines. And we're in gravity pipe here on this tab. Cover, we've approximated a table here of cover by pipe size based off of our Appendix C cover tables. But should folks want to edit this, this is all can be hard-coded in here. The checkbox for consider cover along pipe length is checked. For slope, these calculate that same clearing velocities for minimum 2.5 feet per second and maximum the 15 feet per second. So it's just full flow slopes. And tractive stress is not necessarily something that's considered in our designs here. So under extended design, we've got part full. So know if it's going to design, it's going to design for the pipe to be flowing full. Number of barrels, checking the box for yes, multiples are allowed. And at most, we're going to allow 4. And section size, so that's our maximum pipe size is 120 inches. So no changes so far. This is just review. For node, the preference is to match pipe crowns, and match line offsets just set at 0. And if we do an automatic design, the minimum drop depth at 1 foot will set the invert of the structure bottom 1 foot below the lowest invert of the pipe. And that's more or less It varies based off of the latest standard plans. I think the standard is 6 inches from the outside of the pipe, of the lowest pipe to the structure invert. But this will get us close. So here's where the project-specific information comes in. It needs to know what the maximum spread and gutter depth are. So I think in our example, we said it's a 45 mile an hour design speed, so it gets half of a lane plus a bike lane. There we go. So we're going to enter in a total width of 14 feet and just a 2% cross slope. That'll be 0.28 feet deep. And minimum efficiency on grade, I think we can leave that to 0, but that's if it were going to have a variable opening width of curb inlets and we're going to design the inlet, but that's not how FDOT structures are set up. All right, so that's the end of default design constraints. Next, we're going to take a look at the engineering standards tool. Like I said, it's blank as far as what is delivered, but it's easy to make a new standard here. So the first one I was going to do a sample is like maximum pipe length. So our drainage manual criteria says maximum pipe length is 300 feet for an 18-inch pipe. So we're going to build something that aligns with that. All right, so I think my example is referring to a reference in the drainage manual and giving it a little bit more description on what we're looking for. And we get an option of severity. Is this just FYI only, or is this really an error and we shouldn't allow it to compute otherwise? The element type, so this is pipe. We're going to choose conduit. And we can create a query to say, okay, which of the conduits do we want to check? And it's really going to be just the 18-inch pipes. So we're going to pick a pipe size, which is our conduit diameter. There we go. And if it's less than or equal to 18, all right, so it just told us there are 2 elements where that applies. So that sounds about right with our 2 conduits. All right, and the property it's going to test is the length. And we want to test if it's less than or equal to 300 feet. And that's what will trigger a error, is if we have an 18-inch pipe with a length less than 300. So we can go through and test that. In this case, we know our conduits are, greater than, I didn't see any hand raised, but yeah, minimum 300 or maximum 300, excuse me. So if we wanted to test it, we could change our structure here, the location, to make that pipe longer than 300 feet, and then let it trigger a warning that that's going to be an error. But I'm going to...
So let me add, what does it do? Put up a little like error symbol on the graphics? I mean, what if you change that standard to be like 100 feet? We know they're longer than that.
Right. So let's make sure we get an error. So at 10 feet, if we go to compute, go back to the compute center, you want to do an analysis. There we go.
Were you going to change it from less than to greater than?
That was it. All right, so now I think if we just hit the validate, there we go, one or more errors were found. Then we go to notifications.
Yeah, it does have little information symbols on there.
No, that's for cover. Well, from the course guide, I can show you what it does look like. So we had set the criteria, and if it were violated, it'll tell you one or more of the engineering standards has been violated, and refer to the engineering standards tab. So it'll come up in those notifications. So a little finicky, but it could be useful if there's, overall checks, QC checks people want to do. Engineering standards is the tool that can be used for that. All right. So we've got a basic design and analysis scenario that are already in place, and I think I might have accidentally changed this to design a second ago.
2.
There we go. All right, so in our calculation group, scenario manager will tell us all the scenarios that are there. There's just design and analysis. Those are base level. And if we wanted to make a new scenario, we can tell it if it's a base or child. So if it's a child, it will inherit all of the properties basically as a copy. And if anything changes in the parent, the child sees it, and it will continue to follow the parent properties, with the exception of the one thing that's changed in that child scenario. All right, so we're going to make a new child scenario, and it's going to be for our 4-inch intensity spread storm. So a new child scenario, and we're going to name it very, very descriptively, 4-inch per hour absolute intensity. And we can double click that to see what its properties are. So you'll see that this I in as a preface to this means it's an inherited property, and so there's really nothing different between this scenario and the analysis scenario, and that's not yet. So what we're going to do for the rainfall is to then go to well, from here we can make the change. We can change our rainfall, and instead of just using the inherited base, we can create a new one, which we can also do from the alternatives. So I'm just going to hit OK for this alternative name. So now we've got a new alternative, but we got to fill in the properties of that. So from there we go to our alternatives manager, and all of the alternatives there for now say base, but you'll see under our new rainfall, now we have an updated alternative that we just created. So to double click properties on that, we're going to say no, we don't want this 3-year storm. We want it to be, I think it's at the very bottom here, the absolute intensity. So now we have an alternative that's just giving us 4 inches per hour, and that's global. So that's what we'll use for the spread calculations. And we can also verify what rainfall alternatives are out there by going back to our global storm events. And now it sees that this file has 2 alternatives, the base rainfall runoff and our 4 inch per hour. All right, so I kind of popped into it earlier, but I'm going to give a little bit more description and detail about this compute center. So it has links to some of the other menus that we've already opened up. The scenario manager shows all the available scenarios, alternatives that we were just in, if you wanted to manage it from there. Our calculation options, which are the various calculation properties and settings for the various design or analysis solvers, which are different than the scenarios. The calculation summary, it will bring up the populated diagram, and it just, nothing's there yet because we haven't hit compute just yet. The notifications, which there should have been that engineering standard populated. But the other ones that we may want to address before running compute is to fix some of these warnings. So this first one, time of concentration is less than the minimum TC. So that probably means we didn't, or I didn't enter in a TC when I built that second catchment. So this will let me zoom to, and then it automatically selects it. So at that point, I can go in and fix the warning. So this time of concentration is 0. I need to make it 10. So that warning should go away. The minimum cover constraint, I think we've got a pipe that's pretty shallow there, but I'm recognizing, well, it's going down upon side slope. So the whole thing's not going to have a foot of cover the whole way. So maybe I'm okay with that, and I'm just going to proceed. So once those are the top menus there, the first piece of the window lets you select which scenario you want to run. And I'm going to switch us to the analysis scenario. So it takes a little bit of time if you're switching back and forth, particularly the more alternatives and topology or physical alternatives you're storing in there. It's going to take more time to switch. And so this tells us it's going to run an analysis. It's going to use the GVF rational StormCAD engine. Again, it's an analysis. It's going to use Manning's as a gravity and pressure friction method. So now we're ready to compute this scenario. So it runs through that whole process. It's going to validate everything again. And so it's telling us it ran the Zone 2 3-year storm and convergence was achieved. If we wanted to check out the warning messages, again, we've got that conduit cover doesn't meet. And we've also got a warning about our spread for the 3-year storm. So since that's not the storm we're interested in here, I'm going to ignore that. And it's telling us the tailwater is ignored. So it will kind of find its own setting, whether it's critical depth or whatnot as a default. But if it's also a good reminder, I don't think I set the tailwater in this pond. So I go into the utility properties of the tailwater. We're saying please use a user defined, and it's an elevation 0. So I think the invert of this pipe's at 25, and let's just say 28 as a tailwater there. So now that we've changed it, I'm going to recompute, and at least that warning will go away, but now we may have a few more depending on the system performance. So tailwater is higher than the ground elevation. That makes sense. It's a pond. The cover constraint, we're already aware of. Minimum velocity, it's letting us know the flow is pretty slow in there, but probably not flowing full. But we could check to make sure those pipes are set at the right slopes. Depth of ponding exceeds maximum design constraint. I think we already saw that. And one or more pipes are operating under pressure. All right. The details of the calculation summary, when that button's clicked, this window comes up that gives some overarching little flex tables to say, okay, so in the catchment summary, we've got 2 drainage areas. Here's the flow coming out of it. We've got 2 pipes. Here's their flow, velocity, hydraulic grade line. So a quick look into just the general performance. All right. I think that takes us through exercise 3.4. So now we're going to jump into the flex tables as far as a way to review the performance. So our storm tab equivalent in the flex tables is shown here. And the columns are squished for formatting purposes. But we can also look at the fields that are provided by going to the edit tool there. So it starts out from left to right, looking at from what structure to what structure, what's the pipe length, what's the drainage area going into it, and the resulting flow, comparison of the elevations of the structure to hydraulic grade line, what's the head loss across the pipe, more information about the pipe, the size, the slopes, demandings and velocities and capacities. So this can be exported into a Excel table, which I'm going to have it go to our workset and calculations folder for engineering data. And going to route and open that up. So another quick way to get to our workset folder is in the FDOT tab, has an Explore Directories that will open up your workset. So it makes it nice and quick to get to. So here's our spreadsheet that we just exported. So it can be a little bit easier just to review in this way, but with some handy Excel formatting. So folks can pick out, do we have sufficient HDL clearance? Are we working within a good realm of velocity? Any constraints that or criteria that's not being met is, we've got a good display of that information here. All right, the next thing we can take a look at is the profiles now that we have HGLs calculated. So back to our profile run, we're going to open up the analysis profile. So now we can see our tailwater's been added at elevation 28. So the HGL then is permeated up through the system. And I think we've got options to, again, add a little more customization to the display. However people find it most useful to take a look at it. And that is it for Chapter 3.